All right, so sorry about that. We left off here talking about endo and exo. So what you have to know is this is when you form a bridged bicyclic compound, the groups that are pointing down, I'll put them in a yellow circle now. We call those, or we call that position the endo position. And the groups that are pointing up, we call it the exo position. There is a more proper way of describing endo and exo, which is the endo position. We say it's syn to the larger bridge, or it's on the same side as the larger bridge. This is the larger bridge. So this is on the same side as the larger bridge. And then you say that the exo position is anti to the larger bridge. Anyhow, I just remember pointing down and pointing up. It works just as well at this level. Now, what you might think is, if you remember back when we talked about cyclohexane in general, or sorry, in organic chemistry 1, you might think, well, the endo position, the groups are axial, and so maybe that's less preferred. But it turns out that the endo position is actually the preferred position, and I'll explain that to you. So it says, for our electron withdrawing groups, right? Remember our electron withdrawing groups, which were the carbonyls here and here, okay? It says when those are attached to your dienophiles, they actually end up in the endo position, which is pointing down, okay? Often it says the endo product is the only product. So it turns out if you do this reaction, we could practice drawing our Diels-Alder arrows like this, and this. The only product you get has those two aldehydes pointing down, and so they're in the endo position. Now, if you're wondering, well, why would that be? Okay, well, our book goes into some detail, but not a lot of detail. What he does is this, okay? This is our slide. This is kind of what we go off of, okay? If you go through the endo transition state, and that's shown up here, down at the bottom, this is exo, so don't worry about that yet. When you go through the endo transition state, you see how the pi bonds from the carbonyls are pointing towards where the pi bond was in your diene. What that does is, it says here, it causes a favorable interaction between the developing pi bond. So that's the one that I have the green line here, okay? The developing pi bond and the electron withdrawing substituents, okay? So you have some kind of favorable interaction here and here when you form the endo, son of a gun, when you form the endo product. In the exo transition state, you don't have that. It's just not there, okay? You can see where the pi bond is being formed, okay? And there's no interaction because the carbonyls are too far apart, so there's no interaction there, okay? So that's the explanation. Don't worry, Mr. Dion's not going to ask you to write an essay or provide me an explanation. All you have to know is that if your dienophile is cis, like this, right? This is cis or Z, whatever you want to call it, okay? In that case, both groups are going to be pointing down. If it was trans, then one would be in the endo position, one would be in the exo position, all right? So the endo transition state is lower in energy, right? Why would that be? Because you end up with something that's more favorable, that interaction, right? So the transition state is more stable or lower in energy, I guess, and so it forms faster, right? You have lower EA, therefore forms faster is all you really need to know, okay? The exo is more stable, but again, lower activation energy, and so the endo forms faster, and so that's going to predominate. All right, 16.17, there's a lot to unpack here. It says predict the products for each of the following reactions. So we're starting with a cyclic diene, and here's our dienophile. So first, remember, in the Diels-Alder, you form a ring. So we've already got a ring, so that means we're going to have a bicyclic product, right? So if we draw our curved arrow, so here's our first curved arrow, form our first sigma bond. Here's our second one. We move this pi bond, so let's draw what the product is going to look like. We're going to form a 6-membered ring. Let me prove it to you. Watch. 1, 2, 3, 4, 5, 6. And then you're also going to have the 5-membered ring from your diene, right? So what's that going to look like? You're going to have to practice drawing this a little bit. You're going to have something that looks like this, okay, like that. And we only have one electron withdrawing group, so we're going to draw it pointing down like this in the endo position, right? This is endo. And of course, you could also form the enantiomer of this product. And so we're going to say you're going to get this compound plus it's an enantiomer as well. Okay. Now with the next one, we're starting off with a cyclic diene. So that means we're going to get a bicyclic product. But now we have a carboxyl group here and a carboxyl group here. Those are E to each other. So they're going to be, we're going to have one in the endo position and one in the exo position. And so if we draw our curved arrows, we're going to form a sigma bond, form another sigma bond, and move this pi bond. And our product is going to look something like this. Okay, so we're going to have our two methoxy groups over here. We have our sulfur. We have our sulfur, which is going to be up here like this. Then we're going to have one carboxyl group in the exo position. I'll just put CO2H to condense it. And then we're going to have one in the endo position like this. And of course, we can also form the enantiomer of that compound. The next one, same vein. We're starting out with a cyclic diene, so we're going to get a bicyclic compound. We've got an electron withdrawing group on here. It's going to end up in the endo position. And so try to redeem myself for the bicyclic structure I drew in C maybe. See if I can improve it. So we end up with something that looks like this. Here's our two methyl groups in the back. And our nitrile is going to be going down like this. If you want to be sure, you can draw the proton pointing up. So again, this is the endo position. And then the last one, we're going to get a tricyclic compound, aren't we? Because we've got a cyclic diene, cyclic dienophyte, and we're also going to make a six-membered ring. So if you're like, well, shoot, that's a lot of carbon atoms, connected together. You're right. So let's draw our curved arrows for our Diels-Alder. And now our product is going to look something like this. So I don't have a lot of space to draw it on here, but so we're going to have our bridged compound, our six-membered ring like this. I'm going to have to move this because I'm kind of running out of space. But remember, we're going to get the endo product, okay? So what does that mean? It means that this bond, meaning this bond and this bond, are going to have to be pointing down, okay? So we're going to draw them pointing down. There's my black pen. Go. It's going to be pointing down, and then we have our five-membered ring here. Come on. There we go. Like this and like this. All right, like that. And so if you want to be sure that everybody knows that those bonds are pointing down, you could put in the protons in the exo position. Then, of course, I forgot my oxygen, so I'll put that up here. And there you go. So again, you end up with the endo product in this case. Are you going to have to practice this? Yes, you will have to practice drawing these curved arrows and counting your carbons and everything to make sure that everything connects. All right, so now that we've got that, okay, give me a thumbs up if you're even like 60% of the way with me on these. So I'll make sure I connect this, okay? Even if you're like 60%, you're in good shape because you're going to have to try it, okay? You will have to practice it over and over just like everybody else, okay? It's just a part of life when you study organic chemistry is practicing. Okay, so now that we've got that, if you're wondering, well, what would happen if I had an unsymmetrical diene and an unsymmetrical dienophile? That's a great question. And we actually look at that, okay? And again, I was telling my students before I started recording this lecture that this part here, but getting into the nitty-gritty of the regiochemistry, this is new for the 4th edition of the textbook, okay? This wasn't in the 3rd edition. And so the powers that be have decided that it is important, and so they put it in here. And so let's take a look at regioselectivity. And there's very few examples that we look at. So as long as you understand the ones that we go over in the slides, you'll probably be able to solve anything you would ever have to do in this class. But here we have a symmetrical diene, unsymmetrical dienophyte. You're like, okay, well, that's not too bad. Here I have an unsymmetrical diene. I have a symmetrical dienophyte. Again, there's no differentiation. I can flip this around. I can flip this around. Either way, you're going to end up with the right products. But what if you have something like this? You have an unsymmetrical diene and you have an unsymmetrical dienophile, Okay, in that case, it tells you that when you draw the curved arrows, the predominant way that it's going to react is with the dienophile like this. Okay, this is going to give you the major product, and this orientation would give you the minor product. Okay, so you see here, this is the major product. Now, if you're wondering, why is that? Well, I know that you guys know how to draw resonance arrows really, really well. Okay, so you're going to have to draw some resonance arrows, and that will uncover it for you. Okay, if I was to just kind of back up with you guys and go over some old material with you for just a second, right? If I was to put in the lone pairs on this oxygen and say draw the resonance form, you would say, okay, I'll put a pair here and put a pair here, and then I'm going to end up with a resonance form that's going to look like this. And I have this on another slide, but just bear with me here. Just first, oops, oxygen on the brain. You'd have something that looks like this, where you have a positive charge on the oxygen and a negative charge here, okay, like that. Okay, so you'd have the negative charge over here. So that tells you there's a delta negative here. And if I was to ask you to draw the resonance form of the dienophile, so if I just draw it like this, okay, you would say, well, I could break this bond and I could put this over here. And then you end up with something that looks like this, or have a positive charge here. And so now you can see that if I want the negative and the positive to align with each other, I'm going to have to flip that thing around so that I end up with positive here, right? And then I have this like this. So you can see how this would be the correct orientation. And this explains why you have the methoxy up here and the aldehyde down here like this. Give me a thumbs up if you're even like 20% of the way with me. Trust me, it goes into more detail on my slides, but that's the idea behind it, okay? Is that you've got to draw the resonance forms, okay? So if you have to review, so review resonance, if you have to. If you're like, I don't need to, I know my resonance structures, well then great, okay? Don't worry about it. So, but when you draw the resonance forms for the diene, as I just showed you, you see you have a negative charge here, you have a positive charge here, and what's going to happen is the positive is going to be attracted to the negative, and that's why we end up with a major product when we have an unsymmetrical diene and an unsymmetrical dienophile. So another way of putting it, like I had tried to show you before, is you can just write delta negative and delta plus, and there's going to be a force of attraction between those two, right? Opposites attract. And that's it. And so that explains why you would get your major product like that. So there you go. And now remember, the only time you have to worry about this, drawing these resonance forms, is when both your diene and your dienophile are unsymmetrical. If one of them is symmetrical, just don't worry about this at all. Don't even think about it. It's not going to be anything to worry about. So with that in mind, now we've got some examples where we have 3 unsymmetrical dienes, and then we've got 3 unsymmetrical dienophiles. So I'm going to walk through it with you. And again, there are more practice problems in the textbook that I expect you to give them a shot, okay? It will take you a minute to go through them. Just let me double check here. Yeah, there's one more thing I wanted to show you after this. So let's take a look at the first one. I'm going to probably take a little bit of space up here doing this one. So let's draw our diene, which looks something like this, okay? Oops, can't see my lone pairs. There we go. Okay, so if I asked you to draw the resonance form of this, you would draw something that looks like this. So what we're going to end up with is a resonance form where we have a double bond here, negative charge down here, and we're going to have a positive charge on our oxygen like this. Okay, so we have negative here. And if I was to ask you to draw the resonance form of the aldehyde, you would draw something that looks like this. And so you would end up with something that looks like this. We just drew this a few minutes ago, okay? So it's nothing new, but we'd end up with a positive charge here. And so you can see that it is written in the correct orientation. Here's your positive on your 4 carbons from your diene. And here's, sorry, the negative on the 4 carbons from the diene, okay? The negative is in here. And then we have a positive on the 2 carbons in the dienophile. They're going to be attracted to each other. And so everything is written in the correct orientation here. And so what does that mean? It means we'd say here delta minus, and here we'd say delta plus. And so now we know that we can draw our curved arrows the way that is shown, like that. And so we end up with our product is looking like this. So we have our methoxy group here. Can't see. Our methoxy group here like this. And then we're going to have our aldehyde over here like this. Now, if you're wondering, well, hold on, Mr. Dion, isn't this a stereocenter and this a stereocenter? You're right, they are. They absolutely are. However, that's beyond the scope of our textbook. We don't worry about it. All I care about for the regioselectivity is that you have the diene and the dienophile in the correct orientation. If you can do that, it's good enough for this guy, okay? So there we go. So I'm going to erase this because this is shown in the solutions manual. I'm just going to erase my work here. So I'll just delete it and I'll put the product up here like this. For the next one, let's see if we can do it a little bit quicker. A little quicker. I'll put the lone pairs in here. You know that you could draw a resonance form like this. So that would mean that you would have a delta negative here, right? And if we draw the triple bond to the nitrogen, we could draw one like this. And so that means we're going to have a delta plus here. So it's drawn in the correct orientation again. Again, you can't depend on that, but it is drawn in the correct orientation. So we can draw our Diels-Alder curved arrows like this. And then we can draw our product, which looks like this. We have our methoxy group over here, and then we have our nitrile here. Again, yes, there's a stereocenter right here in the compound. Don't worry about it. I'm not going to ask you, is this racemic or anything like this? The next one, again, in the same vein, if I put in my lone pair, tell me that didn't everything. Shutter. All right. So the next one, so the first one, the product was what? For the first one, the product was this. So we had this. There we go. For the next one, we had this. So we had our methoxy group over here. Then we had our nitrile over here. And the reason why is because this is delta negative, this is delta plus, this is delta negative, this is delta plus. And this one, the last one, we'll put our lone pairs in here and we could say, well, you've got a resonance form here, so you've got a delta negative here. And then for this one, if you drew the whole ester out like this, you could say, well, I've got something like this. And so if you do that, you end up with a delta plus here. So you can see that you've got to flip this one around. So you'd actually have to draw the dienophile like this. Okay, and we wouldn't react with it in this orientation. We'd react with it in this orientation because you have your delta plus here. So we can draw our curved arrows like this, this, like this, and then we'll try to draw the product. It's going to be bicyclic in this case. So we'll end up with our 5-membered ring. We're going to have our ethoxy group over here like this. And of course, our ester is going to be pointing down in the endo position because of the endo rule and that favorable interaction. Sorry, what am I talking about? There's no endo in this case. The carbon's sp2. Mr. Dion forgot about his pi bond. There we go. So there you go, my friends. That's how regioselectivity works. So again, if you need to review resonance, review resonance. If necessary, just take a quick peek. It's covered in chapter 2. If you're rusty on it, just take a look at chapter 2. The whole thing's in there from soup to nuts, and that'll give you everything you need to do there. All right, give me a thumbs up if you're with me on regioselectivity. Even if you're with me part of the way, we'll be sitting pretty. Cha. All right, good. Okay, so there's only 2 more parts left, 2 more questions really. The next one is just kind of standard Diels-Alder stuff. So I'm going to go over 2 of these problems with you. I'm going to go over the first 2 with you, just these 2. And I want you to try the next 2, C and D, on your own. And again, the solutions are in the solutions manual. But the main thing is that you want to practice drawing the mechanism over and over so that you don't make any mistakes on your connectivity. Now, again, your diene is cyclic, so you're going to end up with a bicyclic structure. But now you've got two six-membered rings. So you end up with something, I was trying to use my black pen. There we go. So you end up with something that looks like this, where you have a six-membered ring, not a five-membered ring, but a six-membered ring, and another six-membered ring like this. Here's the pi bond in the back. But since this is E, you're going to end up with one of those carboxyl groups in the exo position, and you're going to end up with one in the endo position like this. And of course, you'll also end up with the mirror image that is non-superposable, so the enantiomer. In B, again, you have a cyclic diene, and these two groups are Z to each other, so they are zusammen to each other. So they're both going to be in the endo position. So for this one, we're going to end up with a bicyclic compound, but our bridge is only going to have one carbon in it because our diene has only 5 carbons in the ring, not 6. So we're going to draw something that looks like this, maybe a little better, something like that. And now we're going to have the carboxyl group is going to be pointing down, and the cyano group is going to be pointing like this. So remember, these are both endo because endo rule. Okay, that's my explanation. It's just because of the endo rule. They're going to be pointing down, and of course, you're going to end up with the enantiomer here as well. So the last two, I want you to try those on your own. So make sure you try these. And the last one, this is a classic. You can see I stuck the question up here. It says, identify the reagents that you would need to prepare each of the following by a Diels-Alder. This is a real classic from the ACS, MCAT, DAT exam. Any of those standardized exams, they love this question, okay? Where they want you to draw the mechanism of the retro Diels-Alder. That's all they're asking for is draw retro Diels-Alder mechanism. That's all you have to do. So the same old 3 arrows, just in reverse now. So look, do 1, 2, 3. That's it. If you can draw the product of those 3 curved arrows, you're going to end up with the product. Let's try it. So if we draw what we end up with, we're going to remember, we're breaking this bond and this bond, right? Those bonds are gone, okay? And the 2 carboxyl groups are both pointing up, so that means we have a Z dienophile. So we end up with a Z dienophile, right? Zusammen, together, okay? So there's our dienophile, and our diene is just going to be this, and then we've got our 2 methyl groups here. So there you go. Those are the starting materials. Now for the next one, students will sometimes say, do I draw the mechanism in this ring or in this ring? It's the one I have the arrows around now, right? Because you've got to break this bond and this bond, because this is where your dienophile comes from. It comes from this portion right here. So when you draw your curved arrows, you have a new pi bond here. You break this sigma bond, and then you break this sigma bond. So yes, your diene is going to have 6 carbons in it, right? 1, 2, 3, 4, 5, 6. Okay, so when we draw our diene, it's going to be a 6-membered ring. Okay, and if you're like, isn't that just 1,3-cyclohexadiene? Yes, we've drawn it over and over today. And then your dienophile is going to be this tetracyanoethylene. Okay, I mean, that's got 4 electron withdrawing groups. Is that a powerful dienophile or what? That's like the most powerful dienophile in the universe, okay? The next one, again, same rationale. This is where we draw a retro Diels-Alder reaction. We form a pi bond here. We break this bond. We break this bond. So now our diene is going to be cyclopentadiene, that same old 5-membered ring that we've seen a bunch of times today. And what is our diene going to look like? Sorry, our dienophile. I keep mixing up the 2. But anyhow, it's going to be, so since they're both pointing down, right? That means it's going to be a Z compound. So we're going to have one aldehyde here and the other aldehyde here. And then for the last one, we've got a tricyclic compound. And so we're going to end up with two ringed structures for our diene and our dienophile. So we end up with something that looks like this, this, and this. Again, just doing our retro Diels-Alder. And here's what our diene looks like. It's a 5-membered ring, but now you've got an oxygen in the ring. Oops. This. And our dienophile is going to be this compound. This is called maleic anhydride. The name's neither here nor there, but it's a common reagent in organic chemistry. And there you go. So this is practicing drawing their retro Diels-Alder. And again, for my students who are interested in things like MCAT and DAT and those kind of things, it's one of the questions they love to ask is they just give you the product and say, well, what would the starting materials be? Okay. So one of the things they'll give you as an answer to try to throw you off for something like this is they'll give you the tetracyanoethylene. So they'll do something like this because students usually don't mess that up. But then for your diene, they'll give you this instead, right? They'll leave out 2 carbons. And so obviously this is wrong. So I'm going to put an X through it. But that's one of the ways they try to test your knowledge on it. Is they're like, oh, it's just 1,3-butadiene. That's what you use for a Diels-Alder every time, but that's not it. So again, like I told you, if you go into our textbook, and I don't have mine open, so just bear with me here. I just closed it before class today. If you go in our textbook, in chapter 16, we skip 16.8 all the way down to 16.13. Okay, you're not going to be tested on any of that. However, I would say it's an FYI. FYI, if you want to read it, you don't have to. Again, I'm not going to quiz you on it, so don't stress about it. That's for sure. But if you're interested in things like color and I don't know, maybe some other reactions, usually students aren't because we're kind of full of reactions at this point. Okay, you've covered quite a few up to this point, so there's no real need to cover more. But if you want to, you could always do that. But again, you will not be tested on any of those.